I want to make a claim that sounds absurd. Not poetically absurd, not philosophically provocative, but physically precise, mathematically derivable, and grounded in the same general relativity that has been confirmed by every cosmological observation ever made. The claim is this: by the standard definition of a black hole in general relativity, the observable universe satisfies the criteria. You are, right now, inside something that meets the mathematical conditions for a black hole. You have always been. You will always be. I want to take you through the physics of this carefully because there are several ways to misunderstand it and one precise way to understand it correctly. The misunderstanding I most want to avoid is the idea that this is a metaphor, a loose analogy, a way of saying the universe is curved or dense. It is not. It is a specific mathematical statement about the relationship between the mass-energy content of the observable universe, the radius of the observable universe, and the Schwarzschild radius, the quantity that defines the boundary of a black hole. Let me start with the Schwarzschild radius because it is the key to everything. In 1916, Karl Schwarzschild, working at the Russian front during the First World War, found the first exact solution to Einstein's field equations. Einstein had published the general theory of relativity in November 1915, and Schwarzschild solved the equations for the simplest possible case: the space-time geometry outside a spherically symmetric, non-rotating, non-charged mass. He sent his solution to Einstein from the front. Einstein replied that he was surprised the problem could be solved exactly. Schwarzschild died 4 months later from an illness contracted at the front. The Schwarzschild solution describes the geometry of space-time around a spherical mass m. The metric, the mathematical object that describes distances in space-time, takes a specific form that reveals the structure of space-time at every distance from the mass. Far from the mass, the metric approaches flat space-time. Closer to the mass, space-time is curved, and the curvature increases with decreasing distance. At a special radius, the Schwarzschild radius Rs equals 2gm divided by c squared, where g is Newton's gravitational constant and c is the speed of light. At this radius, the metric has a coordinate singularity. The time component of the metric, which governs how clocks run at different distances from the mass, goes to 0. A clock at the Schwarzschild radius runs infinitely slowly compared to a clock at infinity. From the outside perspective, events at the Schwarzschild radius take infinite time to occur. More physically, the escape velocity at the Schwarzschild radius equals c. An object at the Schwarzschild radius would need to travel at c to escape the gravitational pull. Since nothing can travel at c except light, and even light cannot quite escape, the Schwarzschild radius is the boundary of no return. It is the event horizon of a black hole. The coordinate singularity at the Schwarzschild radius is not a physical singularity. It is an artifact of the coordinate system, analogous to the coordinate singularity at the north and south poles of a sphere when using latitude and longitude. In different coordinate systems, developed by Kruskal and Sekaras in the 1960s, the Schwarzschild radius is a smooth part of space-time. An infalling observer would cross the Schwarzschild radius without noticing anything unusual locally. The space-time curvature at the Schwarzschild radius of a large enough black hole can be negligibly small. The event horizon is globally defined, not locally detectable. For the Sun, the Schwarzschild radius is approximately 3 kilometers. If you compressed all the mass of the Sun into a sphere, 3 kilometers in radius, it would be a black hole. The actual Sun has a radius of 700,000 kilometers, far larger than its Schwarzschild radius. For the Earth, the Schwarzschild radius is about 9 millimeters. For a human being of roughly 70 kilograms, it is about 10 to the minus 25 meters, far smaller than a proton. For the supermassive black hole at the center of the Milky Way, Sagittarius A, with a mass of approximately 4 million solar masses, the Schwarzschild radius is about 12 million kilometers, roughly the distance from the Sun to Mercury. The event horizon of Sagittarius A, as imaged by the Event Horizon Telescope collaboration, corresponds precisely to this Schwarzschild radius. Now let me calculate the Schwarzschild radius of the observable universe. The observable universe has a radius of approximately 46 billion light years, or about 4.4 times 10 to the 26 meters. The total mass energy content includes ordinary matter, and dark energy. The critical density of the universe, the density at which space-time is exactly flat, is approximately 9.47 times 10 to the minus 27 kilograms per cubic meter. The observable universe has a volume of approximately 4 times 10 to the 80 cubic meters. Multiplying density by volume gives a total mass energy of approximately 3.8 times 10 to the 54 kilograms. Now, apply the Schwarzschild formula. R. S equals 2 times 6.67 times 10 to the minus 11 times 3.8 times 10 to the 54 divided by the square of 3 times 10 to the 8. Work through the arithmetic. The numerator is approximately 5.07 times 10 to the 44. And the denominator is 9 times 10 to the 16, giving a Schwarzschild radius of approximately 5.6 times 10 to the 26 meters. The radius of the observable universe is approximately 4.4 times 10 to the 26 meters. The Schwarzschild radius of the observable universe's mass energy is approximately 5.6 times 10 to the 26 meters. These numbers are the same order of magnitude. They differ by a factor of roughly 1.3. This is not a coincidence. It is a consequence of the fact that the universe is very close to the critical density. The critical density is defined as the density at which the universe is spatially flat, meaning the total energy exactly balances the expansion. At the critical density, the Friedmann equation gives a specific relationship between the Hubble constant and the density. Working through the algebra, it can be shown that at the critical density, the Schwarzschild radius of any sphere is equal to the Hubble radius of that sphere, the distance at which recession velocity equals c. The observable universe, with its density very close to the critical density, has a Schwarzschild radius approximately equal to its actual radius. What does this mean? By the standard Schwarzschild formula, the observable universe meets the condition for being a black hole. Its mass energy, distributed over its volume, is such that the escape velocity at its boundary equals the speed of light. Now let me address the most important objection immediately, because it is a serious one that reveals something deep about the relationship between the cosmological and astrophysical cases. The objection is this: the interior of an astrophysical black hole is a region where gravity is overwhelmingly dominant, where matter is being crunched toward a singularity, where space-time curvature is extreme. The observable universe is nothing like this. It is a relatively smooth, slowly expanding space. How can it be a black hole? The answer requires understanding the difference between the Schwarzschild black hole and the more general concept of a trapped region in general relativity. Let me be precise about this, because the distinction is fundamental. The Schwarzschild solution describes the space-time outside a static spherical mass. Its interior, extended through the Kruskal-Shekharez coordinates, is a dynamic region that collapses toward a singularity in a finite proper time. The interior is highly curved, and the motion of matter is towards smaller and smaller radii. This is the astrophysical black hole we usually picture. But the defining mathematical property of a black hole event horizon is not the curvature inside. It is the fact that null geodesics, the paths of light rays, do not escape to infinity. An event horizon is the boundary of the region from which no future-directed null geodesic reaches arbitrarily large distances. It is defined globally in terms of the causal structure of the entire space-time, not locally in terms of the curvature at any specific point. This global definition has a crucial property. The event horizon can be smooth, flat, and completely unremarkable locally. The principle of equivalence in general relativity guarantees that any small enough region of space-time looks like flat Minkowski space-time regardless of the global curvature. At the event horizon of a sufficiently large black hole, the tidal forces, the difference in gravitational acceleration between the head and feet of an infalling observer, can be negligibly small. For a stellar mass black hole of a few solar masses, the Schwarzschild radius is a few kilometers, and the tidal forces at the horizon would tear any human-scale object apart. But for a supermassive black hole of a billion solar masses, the Schwarzschild radius is a few billion kilometers, and the tidal forces at the horizon are so weak that a human could cross it without any sensation at all. The horizon of a billion solar mass black hole is gentler than Earth's gravity. For the cosmological black hole of the observable universe, the Schwarzschild radius is 46 billion light years, and the tidal forces at the cosmic horizon are essentially zero. An observer at the cosmic horizon would feel nothing special. There is no wall, no barrier, no sign that says you have crossed the point of no return. The horizon is defined globally by what happens to light rays propagating outward over infinite time. Locally, nothing is unusual. This is the key insight. You cannot feel the cosmic horizon. You cannot detect it with any local measurement. It is a global feature of the causal structure of space-time, but it is real. Light from beyond the cosmic horizon cannot reach you. Events beyond it cannot influence you. You are inside it. The boundary is an event horizon by definition. The inside of this cosmological black hole is not like the inside of an astrophysical black hole in many ways. The matter is not collapsing toward a singularity. Space-time is not highly curved. The local physics is perfectly ordinary, but it shares the defining feature of every black hole: causal isolation. We are inside, and there is no signal that can go out. There is one more crucial difference between the astrophysical and cosmological cases that I want to address, which is the direction of time. Inside an astrophysical black hole, the future direction points toward the singularity. Once inside, the infall toward the singularity is as inevitable as the passage of time itself. Time in the interior runs toward the singularity. In the cosmological case, the situation is reversed. We are inside the event horizon, but the interior is not collapsing, it is expanding. The future direction points away from the singularity, not toward it. In the astrophysical case, the singularity is in the future of the interior. In the cosmological case, the singularity, if there was one at the Big Bang, is in the past of the interior. The two cases are related by a time reversal. This time reversal is not a coincidence. The universe is, in a precise mathematical sense, a time-reversed black hole. A black hole has matter falling in and a singularity in the future. A cosmological universe has matter expanding out from a singularity in the past. The mathematical description of one can be transformed into the other by reversing the time coordinate. This is one of the reasons the connection between black holes and cosmology runs so deep in theoretical physics. This is the precise physical statement. The observable universe is, by the Schwarzschild criterion, a black hole, and we are inside it, experiencing the time-reversed version of gravitational collapse. Now let me take you to the specific work of physicists who have developed this idea most carefully, because this is not just a rough numerical coincidence. It has been studied seriously in the context of several theoretical frameworks. The physicist Lee Smolin, currently at the Perimeter Institute for Theoretical Physics, proposed in 1992 a model called cosmological natural selection. The model begins with a specific hypothesis about what happens inside black holes. Rather than simply reaching a singularity at which physics breaks down, Smolin proposed that the matter compressed to extreme densities inside a black hole eventually bounces, producing a new expanding region of space-time, a new universe. This new universe begins in a hot, dense state like the Big Bang, with physical constants slightly varied from those of the parent universe due to quantum fluctuations during the bounce. The result is a structure analogous to biological evolution, a universe that is finely tuned to produce many black holes, has many offspring universes. A universe that produces few black holes leaves few descendants. Over cosmological generations, the distribution of physical constants evolves toward values that maximize black hole production. The constants of nature are not arbitrary. They are the product of a selection process operating over many generations of universes. Smolin has argued that the physical constants of our universe are in fact close to optimal for black hole production. Small changes in the values of the strong coupling constant, the proton to electron mass ratio, or the cosmological constant, would produce fewer black holes. This is a testable prediction. If cosmological natural selection is correct, we should not be able to vary the constants significantly and increase the number of black holes. The prediction is controversial, and its testing requires a precise model of black hole formation across the range of possible constants. The specific implication for our discussion is that if black holes give birth to new universes, our own universe might be the interior of a black hole that formed in a parent universe. The Big Bang singularity would correspond to the singularity at the center of a black hole. The boundary of our observable universe would correspond to the event horizon. We would be living inside a black hole's interior, seeing only the expanding region that formed from the bounce. The physicist Nikodem Popławski at the University of New Haven has developed this idea in a more rigorous mathematical framework. Popławski uses the Einstein-Cartan theory of gravity rather than standard general relativity. Einstein-Cartan theory extends general relativity by including torsion, a quantity related to the intrinsic spin of matter, in addition to curvature. In the presence of torsion, the collapse of matter does not reach a true singularity. The extreme densities generate a repulsive effect through the spin-torsion interaction that prevents the collapse from reaching infinite density. Instead, the collapse reaches a maximum density and then rebounds, producing an extremely rapid expansion. Popławski has published detailed calculations showing that this rebound can produce an expanding region of space-time with the properties of a Big Bang. The new universe begins hot and dense, then expands and cools, forming structures similar to those we observe. The physical constants of the new universe depend on the properties of the black hole in the parent universe. Different black holes produce different universes with different constants. In Popławski's model, our Big Bang was the bounce inside a black hole that formed in a parent universe. The matter and energy of our universe came from the matter that fell into the black hole. The observable universe is the interior of that black hole, still expanding from the original bounce, bounded by the event horizon that is the cosmic horizon we observe. There is a specific and profound implication here for the arrow of time. In Popławski's model, the black hole in the parent universe has a time direction defined by the collapse of matter toward the center. Inside the new universe produced by the bounce, the time direction is reversed. Matter expands outward rather than collapsing inward. The arrow of time in the new universe is the time reversal of the arrow of time in the parent universe at the point of collapse. This provides a natural explanation for the low entropy of the Big Bang. The Big Bang's extraordinarily ordered initial state, with its vanishingly small entropy relative to what is possible, is not an inexplicable brute fact about the universe. It is a consequence of the dynamics of the bounce. The high entropy collapse state of the black hole's interior is transformed into the low entropy initial state of the new universe by the time reversal involved in the bounce. The arrow of thermodynamics in our universe is the time reversed arrow of the collapsing matter in the parent universe. These models are speculative and face significant challenges. The Einstein-Cartan theory differs from standard general relativity in ways that are difficult to test observationally. The cosmological natural selection model makes specific predictions about the values of physical constants that are difficult to verify without a precise model of black hole formation rates. Neither model is accepted as correct by the majority of physicists. But they illustrate that the idea of our universe being inside a black hole is not merely a numerical coincidence, but has been developed into specific, internally consistent theoretical frameworks by serious physicists working within the mainstream of theoretical physics. The structural similarity between the interior of a black hole and the observable universe is deep enough to motivate detailed theoretical work. Let me describe another line of thinking that connects black holes to the universe's origin, which comes from the holographic principle and the AD-CFT correspondence. The holographic principle, as I described in the Information Universe video, says that the information content of a region of space is bounded by the area of its boundary measured in Planck units. A black hole of a given mass has an entropy, measured in bits, equal to exactly 1/4 of the area of its event horizon in Planck units. This is the Bekenstein-Hawking entropy formula. The holographic principle generalizes this. Any region of space has a maximum information content bounded by its boundary area. This seems paradoxical. The information content of a three-dimensional volume seems like it should scale with the volume, not the area. A library with twice the floor area should hold 4 times the books if we add more shelves, not 2 times. But in the presence of gravity, packing more information into a volume eventually leads to gravitational collapse. Before you can exceed the holographic bound, the region collapses into a black hole. The maximum information content of a region is therefore determined by the area of its boundary, because that is the maximum you can have before collapse. The AD-CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete realization of holography. It says that a theory of quantum gravity in a specific curved space-time called anti-de Sitter space is exactly equivalent to a quantum field theory without gravity on the boundary of that space-time. The bulk physics, including gravity, black holes, and the geometry of space-time, is completely encoded in the boundary theory. The three-dimensional bulk is described by the two-dimensional boundary. The universe has a holographic description. Anti-de Sitter space has a negative cosmological constant, which curves the space-time inward, creating the equivalent of a boundary at infinity. Our universe has a positive cosmological constant, dark energy, which drives the expansion. Our universe is de Sitter space, not anti-de Sitter space. The holographic properties of de Sitter space are less well understood than those of anti-de Sitter space, and extending the AD-CFT correspondence to de Sitter space is an active area of research. But the qualitative picture that emerges from ADS-CFT that the interior of a causal region has a holographic description on its boundary applies to both cases. The interior of a black hole is described by information on its event horizon. The interior of the observable universe may be described by information on its cosmic horizon. The cosmic horizon is to the observable universe what the event horizon is to a black hole. This structural parallel goes deeper than just holography. In AD-CFT, the interior of the spacetime, including the geometry of spacetime itself, emerges from the boundary quantum field theory. The spacetime geometry is not fundamental. It emerges from the entanglement structure of the boundary theory. The bulk is, in a precise technical sense, a derived rather than a fundamental object. If this applies to the observable universe, then the space-time we inhabit, the three-dimensional expanding space in which galaxies and stars and planets exist, is itself an emergent phenomenon arising from quantum information processes on the cosmic horizon. The universe is not just inside a black hole by the casual criterion of being a region from which light cannot escape. It is inside a black hole in the deeper sense that its interior physics is the holographic encoding of boundary physics at the cosmic horizon. This is speculative when applied to de Sitter space rather than anti-de Sitter space. The precise de Sitter holographic correspondence has not been established with the same rigor as AD-CFT, but the research program of de Sitter holography, pursued by theorists including Andrew Strominger at Harvard, points toward a picture in which the observable universe's physics is holographically encoded on its cosmic horizon in exactly the same way that a black hole's physics is encoded on its event horizon. The connection between black holes and cosmology at the level of holography is one of the most active and most promising areas of theoretical physics today. It suggests that the observable universe and a black hole are not just superficially similar, related by a numerical coincidence in the Schwarzschild formula. They are the same structure, described by the same physics, at different scales and with different boundary conditions. Now let me take you to what I think is the most personally significant and most intellectually disturbing implication of all of this. You are inside a structure that satisfies the mathematical criteria for a black hole. The cosmic horizon, the boundary at approximately 46 billion light years in every direction, is an event horizon. Events beyond it are causally disconnected from you. Nothing that happens beyond the cosmic horizon can ever affect you. Nothing you do can ever affect anything beyond the cosmic horizon. You are causally isolated inside the observable universe in exactly the same way that an object inside an astrophysical black hole is causally isolated from the exterior. Let me dwell on what this causal isolation means in practice, because I think its full implications are rarely stated clearly. Every experiment you can ever perform, every observation you can ever make, every inference you can draw about the universe is constrained to the interior of the observable universe. The cosmic horizon is the absolute limit of knowability, not just the limit of what we have observed or what we can currently observe, but the limit of what it is even in principle possible to know about. Beyond the cosmic horizon, events are happening, presumably. Galaxies are evolving. Stars are forming and dying. If the universe is much larger than the observable part, there are regions out there containing the same physics we observe here, and they are evolving in ways that are, in principle, forever inaccessible to us. This is a fundamental epistemic constraint, not just a technological one. It is not that we do not have powerful enough telescopes to see beyond the cosmic horizon. It is that no information from beyond the cosmic horizon can ever reach us. The expansion of space is carrying those regions away faster than light. Any signal they send moves toward us at sea, but the space it must cross is expanding faster, so the signal never arrives. The causal isolation is absolute. Now consider what this means for the simulation hypothesis, which I discussed in The Universe as Computer Video. If the universe is a simulation, the simulators only need to render the interior of the cosmic horizon, because nothing outside can ever be observed or measured from inside. The observable universe is a causally closed domain. Its self-consistency can be maintained without computing anything outside it. The cosmic horizon is not just the boundary of what we can see. It is the boundary of what needs to exist for the simulation to be internally consistent. This is also relevant for the question of whether the universe is fine-tuned. The fine-tuning problem asks why the physical constants of the universe are so precisely set to values that allow for the existence of stars, planets, and life. In the multiverse picture, there are many universes with different constants, and we find ourselves in one with life-permitting constants, because those are the only ones in which we could exist. But in the causal isolation picture, the multiverse, if it exists, is entirely beyond the cosmic horizon. We can never observe it, never test its properties, never confirm that other universes with different constants exist. The multiverse is, in principle, beyond the boundary of what physics can address. This is not just a philosophical limitation. It has practical implications for the methodology of physics. Predictions about the multiverse, predictions that require the existence of regions beyond the cosmic horizon, are not testable in any conventional scientific sense. They are extrapolations of our theories beyond their observational domain. They may be correct, they may be the best theoretical framework we have, but they involve assertions about what exists outside the black hole we are inside, and those assertions cannot be confirmed or refuted by any measurement we can make. I raise this not to dismiss multiverse theories, but to locate them correctly in the epistemic landscape. We are inside a black hole. Its boundary is the cosmic horizon. What we can know is what is inside the boundary. What lies outside is speculation, however well motivated, however mathematically rigorous. Now let me come back to the claim I made at the beginning and address it with the full precision it deserves. You were inside a black hole when you were born because the observable universe was already a black hole when you were born. The Schwarzschild radius of the observable universe's mass energy exceeds the radius of the observable universe. The cosmic horizon at the boundary of the observable universe is an event horizon by the global definition. Light from beyond it cannot reach you, events beyond it cannot influence you, and you are inside the causal boundary. The critical density of the universe at any epoch in its history produces a Schwarzschild radius comparable to the Hubble radius at that epoch. You have always been inside an event horizon, and you still are, because nothing has changed. The observable universe is still approximately at the critical density. The Schwarzschild radius of its mass energy is still approximately equal to its actual radius. The cosmic horizon is still an event horizon. The causal isolation is still complete. The difference between being inside a stellar mass black hole and being inside the cosmological black hole of the observable universe is a difference in scale and in the direction of space-time geometry. Inside a stellar black hole, the geometry drives matter toward a singularity in the future. Inside the cosmological black hole, the geometry drives the expansion of space into the future. Both are consequences of the Einstein field equations applied to regions of space-time from which light cannot escape. The physics is the same, the scale is different, the direction is different. The experience is radically different, but the mathematical structure is identical. You are inside a black hole. The physics says so. The mathematics says so. The measurements of the observable universe's density and radius say so, and there is no way out. Not because the walls are too thick or the gravity too strong, because outside has no meaning from inside. The boundary is not a wall, it is the edge of causality. Beyond it, information cannot travel. Physics as you know it cannot be tested. We are here, inside, and the universe we see is all the universe we will ever have direct access to. The causal structure of space-time has drawn a circle around us, and we are the contents. And the circle is an event horizon, and the name for a region bounded by an event horizon is a black hole. You have always been inside it, you will always be inside it, and the most extraordinary thing about this is not the name we give to the boundary or the structure it implies. The most extraordinary thing is that a piece of the interior of this black hole, a specific configuration of matter and energy assembled from the atoms that fell in at the beginning, has organized itself into the ability to figure this out. The universe gave rise to observers who discovered they are inside a black hole. That may be the most improbable sentence in the history of physics. If this changed how you think about your location in the universe, if the inside of a black hole looks different after understanding that the criteria are satisfied by the region you have always inhabited, tell me in the comments. Tell me whether the causal isolation of the cosmic horizon disturbs you, or whether the fact that it exists changes nothing about your experience of the universe within it. Tell me whether the cosmological natural selection model, or Popławski's bounce cosmology, strikes you as a plausible explanation for the specific properties of our universe. And subscribe if you want to keep going into the places where the physics of black holes and the physics of cosmology reveal themselves to be the same physics seen from different scales in different directions.